Our first algorithm for segmentation is called k-means. The idea here is pretty straightforward. We are looking for k segments in the image. So we take our image and we map it to feature space. And in this feature space, we want to find k clusters. And we find the k clusters by finding the means of the k clusters. So let's take a look at how this works in the case of 3 clusters. So we'll call this 3 means clustering. Let's assume that our feature space is 2-dimensional, just for simplicity. Let's assume that these are the points given to us. We want to essentially apply our algorithm and come up with 3 clusters in this case. So the first thing we do is that we randomly generate 3 means or centroids of the 3 clusters that we're looking for. So these are your initial means, the red dot, the green dot, and the blue dot. And now what we do is we create 3 clusters by assigning each feature point to the nearest mean. So this point ends up being assigned to this mean, all of these end up getting assigned to this mean, and all of these end up getting assigned to this mean right here. So once we're done with that, we're going to recompute the mean of each cluster. And so the mean then goes from here to here, this one goes from here to here, and this one shifts from here to here. And now we're going to repeat steps 2 and 3 until we reach convergence. Convergence in this case simply means that the means that we have computed, the 3 means, stop moving. They have arrived at 3 points and they cease to move from there. At that point, you can say you have found your 3 clusters. That's it. That's your algorithm. And this can, of course, be generalized to k-means or k-segments. So what you're given here is an image with n pixels, and the number of clusters you're looking for is k. And so what you do is you pick k points in your feature space randomly, and those will be your initial means or centroids of your k clusters. Let's call them m1 through mk. And now for each pixel xj, we're going to find the nearest mean mi to the pixel's feature fj. And once you've found the nearest mean, you're going to assign that pixel to that cluster I, right here. Once you've done that for all the pixels, you're going to recompute the mean for each cluster using the assigned pixels. And if the changes in the locations of the k-means is less than some threshold, you stop. Otherwise, you go back to step 2. That's it. Very simple algorithm, k-means clustering. The only thing that we want to say a little bit more about here is how we initialize this step right here, or step number 1, where we say we randomly pick k points in your feature space. Well, we can possibly do better than that. So we can actually improve on that a little bit. So method number 1 is select k random feature points as your initial centroids or means. And if 2 of them happen to be really close together, then you can just simply repeat that process. That is, you resample. The second method is to select k uniformly distributed means within your feature space, within the range of your distribution. So let's say you have your feature space and you have a bounding box around your distribution. You can uniformly sample your k points from in there. The third method is the preferred method. In this case, what you do is you might use either method 1 or method 2 to pick your initial means. But then after that, you're going to use a small subset of your data. So let's say you had 1,000,000 pixels, that would be 1,000,000 points in feature space. Take 1/100th or even 1,000th of those points, and then you're going to use these initial means to then compute your final means, but use those final means as your initial means before applying the algorithm to all 1,000,000 points. So perform k-means clustering on a subset of pixels, use the result as your initial means when you're applying it to the entire image. So let's take a look at how this works. So here is your image again, your mandrel image, and let's say you say k is equal to 2. Obviously, there's a lot more than 2 segments here, but let's just go with that. Here's your distribution in feature space, RGB space, and it gives you these 2 clusters. Again, the colors assigned here are the average values of the colors of all the points that belong to a cluster. And then you go back and relabel your image, you get these labelings. This is what we would call a segmented image. Not very useful in this case because clearly the original image has a lot more than 2 segments. If you go up to 8 segments, this is what you end up with. And in this case, you get this segmentation right here. Now remember that thus far we've essentially used a very simple feature space, which is your RGB color space. And you can do better than that. So in this case, you have another example. These are peppers. Again, you're using your RGB color space right here, and you end up with these segments. And we said in this case, k is equal to 16, but you see that you have a lot more than 16 regions here. And that's because disjoint regions could belong to the same cluster, right? There is nothing here that precludes this region and this region right here as belonging to the same cluster because you're only using your color values. So this sort of tells you that if you make your pixels richer in terms of their visual characteristics, you can do better in terms of segmentation. And that's what we're showing here. Here you use a 5-dimensional feature space where you have RGB and the location of the pixel, X, Y. So now you're encouraging pixels that are close together to belong to the same region or segment, and for that matter, pixels that are far away as not belonging to the same segment, and you end up with a more reasonable segmentation that looks something like this. So that's your k-means algorithm. It's a very simple, very fast algorithm, and the only sort of caveat here is that one needs to pick the initial number of clusters. So depending on your application, you have to specify k, and it is certainly sensitive to the initial means that you end up picking, the random selection of means. So the initialization process is tricky here, and one needs to give some thought to this. It can also be somewhat sensitive to outliers. That is, if you end up having a small group of outliers and an initial mean was picked close to them, that might end up defining a cluster which is not really a substantial cluster. But it still is a popular and widely used method, k-means clustering.